So let's start now looking at some applications. First application I want to talk about is fluid dynamics. So of course we've talked previously about how vector fields can represent the movement of fluids. So what does that have to do with surface integrals? So what if we have V is the velocity field for a fluid flowing in space? Then, excuse me, then our vector surface integral, the double integral over the surface of our fluid velocity field V dot ds is the flow of the fluid across the surface S in volume per unit time, so cubic meters per second. And you can check the units on that if you like. The velocity is meters per second, and then the ds is in area, so that's meters cubed. So put it together and you get cubic meters per second. Okay, so let's do an example. Water in a pipe is flowing through a net where the water velocity field is V equals xz comma x comma y, and that's in meters per second. And the net has the shape of the hemisphere, x squared plus y squared plus z squared equals 25. And we're going to take y to be positive. So it's that half of the sphere. So let's calculate the rate at which water flows through the net. And we're going to be oriented in the positive y direction. So how do we do this? So first of all, let's write down our basic statements. So first of all, we know that the flow rate is going to be this, double integral of the surface of V dot ds. So we know that in order to calculate this, what we will need is we're going to need to parameterize our, basically we need to parameterize the situation. Start by parameterizing the surface. So since the surface is a sphere, or in this case, part of a sphere, we know that we can use spherical coordinates in order to write down the parameterization. So we take the usual formula for a sphere, and we know this sphere, looking at the formula, has a radius 5, so plug that in. So then we get that the parameterization for our surface S is R equals 5 sine phi cos theta, 5 sine phi sine theta, and comma 5 cos phi. Now, what about the bounds? So remember that we want y to be positive. So that means we're not taking the whole sphere. So we still have phi going from 0 to pi, but we want y to be positive, so that, and the theta values that give us positive y, theta goes from 0 to pi. And again, that one works about the same as polar coordinates. Okay, so now we need to calculate our two tangent vectors, and we will need to we need to parameterize everything. So writing our vector field V parametrically, just plugging in, we get this. Velocity field V equals 5 sine phi cos theta times 5 cos phi, comma 5 sine phi cos theta, comma 5 sine phi sine theta. And that's just from the vector field. Next, we need to calculate our normal vector. So first, you need to take dr d phi, then dr d theta, and then take the cross product. However, notice that we've calculated the normal vector for a sphere a couple times. Therefore, on this one, I'm not going to repeat the calculation. I'm just going to borrow from the previous calculation. It's going to wind up being 25 sine square phi cos theta, comma 25 sine square phi sine theta, comma 25 cos phi sine phi. Now, notice that we've constructed our normal vector, but we have to make sure that it's got the orientation that we want. So it said we want the positive y direction, meaning that for the normal vector, the y component had better be positive. But let's take a look. Here's the y components. Whoop, a bit too far, sorry about that. Okay, so the y component is 25 sine squared phi, that part's always positive, and then sine theta. Now remember that we took theta from 0 to pi, so that's always positive. So this component is always positive, so we do have the proper normal vector. Notice that if this thing was like always negative, then we would need to slap a negative sign in front of n to reverse its direction. That's a fancy thing, we don't have to do it here. Okay, so now we can proceed with the calculation. So first of all, basics, flux integral, double integral over the surface of v dot ds, which we then, skipping the middle step, we know that written parametrically, this is just going to be the double integral over the region of v dot n, that's little n, dA. And now we need to plug in our parameterization and then calculate the integral. So we know that, so plugging in, we know that V is, so basically we have these two vectors and we take the dot product. Taking the dot product gives you, and then simplifying gives you this long expression here. And then dA, our two parameters were phi and theta. So it's just going to be d theta d phi. And again, all boundaries are constants. Theta goes from 0 to pi, phi goes from 0 to pi. You could do it in any order. Here I did it d theta d phi. And I just need to calculate. So first doing the d theta integral. Well, to do this one's got a cos squared theta, you're going to need to use the double angle formula. This one's got a cos theta sine theta. You can do that using a substitution. U equals sine theta and du equals cos theta d theta. And this one over here, well, that's just got a sine theta. You can integrate that directly. All the other stuff with phi, of course, gets treated as a constant. So after doing each of those substitutions, or after doing the necessary substitutions and calculations, that integrating everything winds up being, well, you get this whole thing. So 5 sine cubed phi cos phi, and then after integrating the double angle expression, you get half theta plus a quarter sine 2 theta. And then over here, after doing the substitution, you get sine cubed phi and then half sine squared theta. And then over here, integrating sine theta, of course, you could just get negative cos theta. And then all that was times sine squared phi cos phi. And for convenience, I have taken the constant 125 and pulled it out. And then you just evaluate this as theta, goes from 0 to pi, plug it in, and you get this 5/2 pi sine cubed phi cos phi plus 2 sine squared phi cos phi d phi. And this one isn't actually a straightforward substitution. U equals sine phi, and then du equals cos phi d phi. And then it becomes a pretty easy integral to do. You just get 5/2 pi times 1/4 sine to the 4th phi plus 2 times 1/3 sine cubed phi, evaluated from 0 to pi with the 125 still in front. But when you evaluate it, oh, everything cancels and you just get 0. So this tells you that the net flow, some of it's going through, some of it's coming back. The net flow in this case is actually 0. So now let's take this this fluid flow and let's actually extend it a little bit further. So what if the fluid has a density function, P of XYZ, and that measures the mass per unit volume, kilograms per cubic meter? Well, now throw that in there and what do you get? The double integral over the surface of density P times velocity field v dot ds. That is the flow of the fluid across the surface S, but now it's mass per unit time, kilograms per second. So just to explain that for a second, recall that, recall that trying to get it separately here. Okay, so recall that the v dot ds part, that was in cubic meters per second, but now we're multiplying by density, and that's got units mass per cubic meter. Cubic meters cancel and you get kilograms per second. So it's the flow of the fluid across the surface in mass per time. So let's take a look at how that would go. Okay. So if a liquid with density p kilograms per cubic meter, so we'll just take p to be a constant, is flowing through a net where the fluid velocity field is v, and so that is x comma y comma z. There's your velocity field, and the shape of the net is z equals 4 minus x squared minus y squared. Calculate the rate in kilograms per second at which liquid flows upward through the part of the net above the YZ plane. Excuse me, above the XY plane. So there's the question. So how do we do this? Let's set this up. So the first thing we do is we need to parameterize the situation. But notice that our surface is described by z equals g of xy. So because the surface z is a function of xy, we can use our shortcuts. So we know the shortcut formula for the normal vector is just going to be negative gx comma negative gy comma 1. So in this case, that works out to be 2x comma 2y comma 1. There's your normal vector. And we know that basically we're going to use x and y as our parameters, and we'll just leave it in terms of x and y. Okay, so we know that the flow rate, and again, this is the mass flow rate, not the volume flow rate. The mass flow rate is the double integral over the surface of p times v dot ds, which we know will be written parametrically as a double integral over the region of density p times velocity field v dot normal little n dA. And bring it down a little bit. Okay, there we go. So let's put all that together. So P, density P is just a constant in this case. So I'm just going to pull that out in front. Velocity field was XYZ. And then we have to dot it with the normal, which is 2x comma 2y comma 1. And all of that will be dA. So let's punch that all in and see what we get. So taking the dot product, you just get 2x squared. Well, simplifying, we're going to get 4 plus x squared plus y squared. And so it's going to be p times double integral of the region of 4 plus x squared plus y squared dA. Now, we have to figure out what is the region and how do I want to set that up. So notice that the boundary of the net, let's go back to the question for a second. Here we go. So the boundary of the net, notice that it says above the xy plane. So the boundary is the xy plane, which is where z equals 0. So the surface is z equals 4 minus x squared minus y squared, and then the boundary is where z equals 0. So make that substitution, and what do you get? X squared plus, solving and simplifying, x squared plus y squared equals 4. So how are we going to describe that using coordinates? Simple. Use polar coordinates. So polar coordinates give us our parameterization for the region R. So we want x to be r cos theta, y equals r sine theta, and we want the whole region. So r goes from, let me see. Yes, x squared plus y squared equals 4, so we know our radius is 2. So the maximum radius is 2, so r goes from 0 to 2. And then we're going all the way around, so theta goes from 0 to 2 pi. Further, dA was dx dy, but we know how dx dy converts into polar coordinates. Dx dy becomes r dr d theta. So so this integral converted from xy coordinates over here now into polar coordinates. What do we get? It's equals p times the integral. And here I wrote it as dr d theta. So theta goes from 0 to 2 pi, r goes from 0 to 2. And notice that x squared plus y squared, we have to rewrite this in terms of polar coordinates, but that's really easy because we know that x squared plus y squared is just r squared. So this whole function just becomes 4 plus r squared. dA, which is dx dy, just became r dr d theta. So before we do the integral, of course, we'll distribute the r. So integrating 4r plus r cubed. Integrate that dr now, and you get 2r squared plus plus 1/4 r to the 4th. Evaluate as r goes from 0 to 2. Plugging that in, you just get 12. And now we integrate that d theta. That's 12 theta evaluated from 0 to 2 pi. So that just gives you 24 pi times the constant p. And again, remember this was kilograms per second for the flow of the fluid. Next, let's take a look at electrostatics. And remember, electrostatics is just a fancy term for there's electric charge and it's not moving. So in this case, what does it mean? So the vector field describes an electric field from stationary charge. It's typically written as capital E. So this measures force per charge. So the units are newtons per coulomb, which is also equivalent to volts per meter. So the surface integral, which is written as the double integral over the surface S of E dot ds. Calculates what we call the accumulation of the electric field across S. And just generally, this is called the electric flux of electric field E across the surface S. And the units are a little funky. It's Newton meters squared per coulomb or just voltmeters. So that's the application idea. Let's do a calculation. Okay, so let's talk about an electric field that's got a fixed charge Q at the origin. So the electric field for that, given by Coulomb's law, is E equals KQ over R cubed times R, your position vector, where K and Q are constants. So let's find the electric flux of the electric field E across the surface S, which is, in this case, the sphere of radius A, x squared plus y squared plus z squared equals a squared. And we'll take the usual outward orientation. So let's calculate. First thing we need our parameterization of our surface. Our surface is a sphere of radius A, so we've done this before. R equals A sine U cos V, comma A sine U sine V, comma A cos U. U goes from 0 to pi, V goes from 0 to 2 pi. So now notice in this case, I am using the standard parameterization letters U and V, but U plays the role of phi, and V plays the role of theta. So showing you the calculation again really quickly, even though we've done it before. dr du equals a cos u cos v, a cos u sine v, negative a sine v. Sorry, sine u. And dr dv equals negative a sine u sine v, comma a sine u cos v, comma 0. Take the cross product, Ru cross Rv, to get the normal vector, and you get, as we've gotten before, a squared sine square u cos v, a squared sine square u sine v, a squared sine u cos u. Okay. So now, what is our vector field? Our vector field, which, right, I'm calling E here, equals kq over the magnitude r cubed times our position vector r. So we get this. So again, remember that since we're on a sphere radius a, the magnitude of r, we calculate it, but it's always going to be a. So that's just kq over a cubed, that's one big constant, times our position vector, which was the thing we just calculated, the thing we just, sorry, wrote down our parameterization over here. So if we simplify, and a cancels. Well, stuff is going to cancel anyway. So let's see how that's going to look. So now let's calculate separately. I'm going to calculate the dot product. That should be normal vector n. Sorry about that. Okay, so separately calculating the dot product of the vector field E dot the normal vector little n. All right, so sorry, a little typo. That should be we know we're going to have to calculate the vector field dot the normal vector little n. So I'm calculating that ahead of time now because there's a bunch of algebra and it simplifies. So let's take a look. So here's your vector field E, and here's your normal vector little n. So taking the dot product, you wind up with something nice actually happens. You get an a and an a squared all over a cubed, so all the a's will actually wind up canceling. So you get kq as your constant. And then sine cubed u cos squared v plus sine cubed u sine squared v plus sine u cos squared u. You get the sine squareds and cos squareds for using v's combining, and something nice happens. You actually just wind up with kq sine u. So we've done that simplification ahead of time. Now let's get into writing down the flux integral. So the flux we know is going to be the double integral over the surface of f dot n ds, which we know is going to be the double integral over the region of, sorry, and we're calling our vector field E, it's the electric field. So we know our double integral is going to be, it's double integral over the region of electric field E dot normal vector n dA, but we just calculated vector field E dot normal vector n, and we know it just simplifies to kq times sine u. Okay, so now we've got to do this integral. So we know dA is just going to be du dv, and we have the boundaries for u and v. So once we've done all the prep work ahead of time, this is actually an easy integral. Otherwise, you'd be doing the algebra right now. So the integral of sine u du is just negative cos u, and the boundaries for u were 0 to pi. So plugging that in, you just get 2. And then integrating that dv, you get 4 pi. So, sorry, 2v, evaluate from 0 to 2 pi, you just get 4 pi. Put it all together and you get 4 pi kq. So that's the result of the calculation. Sorry for my typos. Let's take a look at what this says. This says that the flux of the electric field E over the sphere is just the enclosed charge, which was Q, times a constant, which is 4 pi k. So later we're actually going to use this result as a special case. I'm going to show that this is actually true, not just for a sphere. Turns out this is true for any closed surface. Okay. Let's take time to do one more example. Okay, one more application, magnetism. So we'll be talking about a magnetic field. So this measures the intensity of a magnetic force which could act on a charged particle. Now, when we calculate our flux integral, it gives us the magnetic flux. The magnetic flux measures the accumulation of the magnetic field over a surface. So we typically write magnetic field as capital B, and then we say the magnetic flux is our flux integral. So double integral over the surface of magnetic field B dot ds. So for the magnetic field B, the units are newtons per amp meter, and this is also known as the Tesla. The unit for magnetic flux is the volt second, which is also known as the Weber. So, so noting this, you could also use Webers per meter squared as units for the magnetic field, but typically it's just called Teslas. Okay, so let's do an example of a flux integral for magnetism. So for the magnetic field B, which would be, we're taking our field to be x comma y comma 2z, and our surface S, we're going to say z equals 4 minus x squared minus y squared, with bounds x goes from 0 to 1 and y goes from 0 to 1. With the downward orientation, let's calculate the magnetic flux. So notice that our surface is z equals a function of x and y, so we can use the shortcuts. So z equals f of xy, so therefore we know the normal vector is just negative fx, negative fy, comma 1, which in this case is 2x, comma 2y, comma 1. Now, extra wrinkle here. This vector, as we typically construct with z equals f of xy surfaces, our normal vector points up. However, the question specifically says, give your surface the downward orientation. So for that reason, you take your normal vector and you must flip it. So your normal vector is going to be negative 2x, negative 2y, negative 1. And now you've got a normal vector oriented downward. Okay. Okay, so our flux integral to find the magnetic flux is the double integral over the surface of B dot ds. And we know to calculate this, we need the parameterization, which we can write as the double integral over the region, that's the region in our parameters, of vector field B dot normal little n dA. So let's plug that all in and see what we get. So we know our vector field B is x comma y comma 2z, but we know that z is really 4 minus x squared minus y squared. So we have to make that substitution. Dot our normal vector, properly oriented as requested, negative 2x comma negative 2y comma negative 1. So taking the dot product and simplifying, you get this. Okay, so I converted the z at the, you can either convert the z in the beginning or the end. Probably should really do it in the beginning. Okay. So simplifying this, so stuff cancels and you just wind up with negative 8. And now we can write dA as dx dy, and we know the boundaries, x goes from 0 to 1, y goes from 0 to 1. Once you set it up, it's actually a very easy integral to do. And we just think of it as negative 8 times the area, and the area is just 1. So the answer is negative 8. So negative 8 Webers. And for anyone who has an interest in physics, I was always curious about why a magnetic field was the letter B. So a little side note, it turns out that the notation B for magnetic field is a total accident of history. So Maxwell, who's one of the most important physicists ever, wrote a book in which he made a list of vector fields in physics. And he just happened to label them alphabetically, and your magnetic field got B. So let's take a moment to summarize everything that we've done with surface integrals. It's all in this table. So, surface integral. So the first thing always is that you need to calculate your normal vector. So now notice that for this table, I've written down 2 columns because the parametric form, which is on the right, is your general form that you can always use. Now on the left, special case, which is when the surface can be written in terms of z equals f of xy. It comes up a lot, so it's an important special case. So, of course, there's a, formatting. There's a nice shortcut formula for things in when you can write it in terms of z equals f of xy. But in each case, here's how you calculate, first of all, your normal vector, which you're going to need. Next, how do you do a scalar surface integral? So first, you're going to need to know how do you convert your ds parametrically. And in the coordinate, so in either case, you're always writing it as the magnitude of the normal vector times dA. Now, the special case is if you have z equals f of xy, then you know this just converts like this. But in general, it's just whatever the normal vector is, magnitude of that times dA. And if you also have a function in there, then the function is just in there as well. Okay. So that is how you do, that's the overview of how you do a scalar surface integral. Now, what about a vector surface integral? Vector surface integral, you'll need to convert your d of oriented s, which by definition is the same as unit normal big N ds, which we know just converts as normal vector little n dA. Now that's always true. Now in the special case, when z equals f of xy, we know what our normal little n becomes. It becomes negative df dx, comma negative df dy, comma 1. And then, of course, times dA. And that, of course, is assuming the upward orientation. We previously saw a problem where you were requested for the downward orientation, so you had to flip it. Okay. And again, everything except the special case is also true for the parametric form. And then finally, how do you do a vector surface integral? That's just going to be the double integral over your surface of vector field F dot d-oriented S, which by definition is just unit normal n times ds. And we know that parameterizes as the double integral over the region of vector field F dot normal little n dA. Applications, plenty of applications. Surface area, electricity, magnetism, fluid flow, heat flow, and other things as well. But here's the quick summary of all the formulas. And of course, the applications with all the details are things that we've, and step-by-step how to do it, are things that we've just talked about.